We're going to get into 8.4 example 3. I think you're really going to like this. Why don't you take a second and grab your graphing calculator. You are definitely going to miss it if you don't have it. I'm going to show you some really cool keying sequences, and we're going to start putting these guys, these different quadratics, onto our calculators and letting the calculator graph it for us. So I wanted to show you how to do that. So pause me and grab your calculator. Okay, welcome back. I'm going to read the top part of your notes here. The quadratic function h of t equals negative 16t squared plus c can be used to approximate the height. That's what h is. H is height in feet above the ground of a falling object, t seconds. Seconds time is t after it is dropped from a height of c. This model is used only to approximate the height of falling objects because it does not account for air resistance, wind, and other real-world factors. So air resistance and wind produces friction, and so when things are flying through the air molecules are creating friction and actually slowing the object down is what it's doing. We're basically in a perfect environment that's frictionless. There's no air, no wind, no other factors that are creating friction and slowing it down. This is a dropped object, basically in a vacuum, okay? So, just in short, just remember your y-axis is height above the ground. That's what they're telling you. And then your x-axis is time, okay? And what they're giving you, they're trying to show you that when you use this basic formula, they're going to give you information so that you can plug in for C. C is from what height the object is dropped. So kind of think like somebody's at the top of a building holding a ball, and then they suddenly drop it. C is the height that at the moment it was dropped. How high off the ground was it? That's what C is all about, okay? So here's example 3. You have two identical water balloons, and they are dropped from different heights, okay? I don't know if I would drop a water balloon. I definitely would throw it, so at someone. So they're dropping their water balloons. We'll throw it. One was dropped from a height of 64 feet. And the other balloon was dropped from a height of 144 feet. So big difference between the two heights there. So what they want us to do in letter A is they want us to write the two height functions and compare their graphs. So we're pulling from what we learned in example 2 up into example 3. Okay, so here are the two height functions. The first water balloon was dropped from a height of 64 feet. So I'm going to replace C with 64. The second water balloon was dropped from a height of 144 feet. And so I'm going to replace that C with 144. Now, we have our two quadratic functions, and they are asking us to compare their graphs. So remember what we compared before. We discussed the widths. Now they both have A is negative 16, absolute value of negative 16 is 16. They have the same exact absolute value. So both of these graphs would have the exact same width. Okay, so that hopefully you see that very clearly and very easily. Let's talk about the vertical change. Now, we're not starting, this particular graph is not starting at the origin. It's starting at 64 and going up to 144. So what would be the difference or the distance between 144 and 64? We want to know what's the difference between those two numbers, because that's going to give us our vertical change, okay? So when we subtract, we'll see that the second balloon, the one at 144 feet off the ground, is 80 feet higher, okay? So the second water balloon is at a height that is 80 feet higher. Than the first balloon. Okay, so hopefully you saw the real easy math. It's very simplistic math when you're comparing the vertical translation of these two water balloons. You just take the higher height and subtract the lower height from it. And that's the distance between those two heights. And that's the vertical change that happened between the two water balloons. All right, so we compared the widths, we compared the heights, the vertical translation. Now we're going to use the graphs to tell when each water balloon reaches the ground, okay? Now this is where it's going to get really, really super fun. You're going to need your graphing calculator. I'm going to switch over to the camera now. There we go. And my calculator's off, so I'll just turn that on really quick. And you're not going to watch me key necessarily. I'm just focusing on the top portion of my calculator because those buttons are the most important. I trust that you know how to key in numbers, variables, and exponents. Okay, you don't need to watch me do that necessarily. We've done that enough. And what we're going to do is we're going to put in both of these equations into the y equals function, okay? But let's first set up the window. Do you see the second button here from the left called window? I want you to press that, okay? Now your numbers may look different than my numbers. I just actually programmed these in there just a little while ago. What we want to do is we just want to see the first quadrant. We want to see what time did these water balloons land on the ground, okay? And so when you see the graph, I'll kind of explain it a little bit more. But what time do these water balloons land on the ground? So in order to do that, we need to set the minimum x at 0, okay? So do that and then arrow down to the x maximum. We don't need it very big, so just press 5. The scale, I want the x's to go by ones. So press 1 if it's not already there. Now the y minimum, we want to start at 0. We don't really need anything under that because we want to stay first quadrant. Now your y max, you always set this at your highest vertical height. Remember, one of our water balloons was dropped at a height of 144 feet. So that's our highest drop. So we're going to put 144 in. Your y scale, we don't want to go by ones. That will be kind of crazy. So let's go by increments of 10 because 144 is such a big number. Let's skip count a little bit and let the y axis count by tens. The rest of it, the x res, the triangle x and trace step, don't worry about that. Just ignore it. It's not going to affect your graph one way or the other. Okay? So double check your numbers. Make sure your x min, x max, x scale, y min, y max, and y scale all look like mine. Okay? It would be very, very helpful if it was. Okay. Now, I want you to press the y equals button because now we get to tell the calculator exactly what two equations we want it to do. So look at your note packet. We came up with the two equations in letter A of that example. So press -16. I know it says t. We're going to press x squared plus 64. Now mine's a color-coded calculator, so that line's going to show up blue on my calculator. Okay? Now I'm going to arrow down and I'm going to go to the y2. That's going to show up red. And I'm going to do -16x squared plus 144. So there's my two equations. I've already set the window, how I want it to look, and now I'm ready to graph it. So we're going to press the graph button and watch it go. And we're seeing just half of the parabola. And that's okay. I don't need to see the whole parabola. I just need to see half of it. Now notice we're going by ones. So this first notch here on your calculator is 1 second, 2 seconds, 3 seconds, 4 seconds, and way out here is 5 seconds. Remember, we set the X scale to 5. We wanted it to go, not the scale, but the maximum. We want it to go out through 5 and go by ones. The X scale is actually a 1. And so whatever scale you set, that's the increment for each number. So we chose scale of 1, so we're going by ones. On the y-axis, notice there's lots of little notches here. Those are all going by tens because we set the y scale to 10. So the first notch is 10, the second one's 20, 30, 40, 50, and so on. Okay? So what we're looking for, remember the x-axis, I told you the x-axis is time. So the water balloons are going to land at different times because they are at different heights. It's going to take a little longer for one of them to hit because it was dropped from a higher height. So the blue line, remember, that was our 64-foot high balloon. And can you tell from the graph exactly how many seconds it took? Now I hope you're telling me 2 seconds because you're exactly right. Do you know when the red balloon went? And hopefully you're saying, yeah, 3 seconds, and you would be exactly right. So that's a wonderful way. It's a great tool. Sometimes those answers just don't pass through a grid intersection where we can tell exactly what the answer is. And so another trick of the trade is to use the table function. Now if you hit the second button, what we want to do is we want to hit that table function that's above the graph. So if you hit second table, all your data points are there, and you can actually find where your x-intercepts are. Remember, x-intercepts are always a number, and then y is always 0, because we're saying height is 0, it's on the ground. Well, we know it's not going to be negative. We're not going to have a negative height, so I'm just going to bump down, okay? And I'm going to keep going and just kind of bump this down and put a couple of these up so you can see where the heights are 0, okay? So for the blue line, do you see where it says x is 2, y is 0 for the blue line? Well, 2 seconds, x is 2, that means 2 seconds at a height of 0. That's what that means. Now for the red line, you have to skip this middle column, that's all blue data. 3, 0 is the red line. So that means the red line was 3 seconds. It took 3 seconds for it to land. So you could also use the table function if you just really get stuck and you can't see it on your graph. You just can't make the graph work for you. That's a great option, is to use the table function. Okay, now I'm going to switch back to our notes now. Okay, and I think we're right here. So use the graphs to tell when each water balloon reaches the ground. We found that h of t equals negative 16t squared plus 64 reaches in 2 seconds. Remember, that was our blue line, okay? And then our red line, my red line, if you don't have a calculator like mine, we saw that it reaches in 3 seconds. Okay? And so hopefully I gave you some really good calculator clues, and let the calculator help you. It will speed you up. We do some things by hand because I need you to know how to do it by hand in case we don't have a calculator, and then there's other times when a calculator will really benefit us, and it's important to know a keying sequence. Okay, so next page. This one's for you. I'm going to give you extra credit. And this time I'm going to give you 2 points, one for A, one for B. Give it your best shot. See what you can do. Use your calculator and see if you can figure it out. Good luck with that, and bring your questions to class tomorrow.